Good day, Robert Wilson with University of Central Florida Modeling and Simulation Program. This presentation will be covering Module 2, Monte Carlo versus Rule-Based Agents. During this presentation, we'll be covering these contents. We'll be talking about OpenAI Gymnasium from Pharmara. We'll be looking at the Lunar Lander version 2, looking at Monte Carlo versus rule-based models that we developed in Python in Google Colab. We'll look at a Monte Carlo model renderer of one of the Monte Carlo simulation runs. We'll be looking at rule-based model renderer for one of the rule-based runs. We'll also be looking at performance results, some with a horizontal correction applied and some without a horizontal correction applied. The Pharma toolset is built upon the widely recognized OpenAI GYM framework, a foundational tool in the development and testing of reinforcement learning algorithms. This toolset has expanded upon the original GYM environments, offering a broad array of scenarios and challenges and refining reinforcement learning models. The toolset includes a variety of environments, each designed to test different aspects of an agent's capabilities. Let's briefly look at the main categories. The first is the classic control. These are the foundational environments that include simple yet challenging tasks like the cart pull, as demonstrated in the image here, and the mountain car, which are often used as benchmarks in reinforcement learning research. Second is the box 2D. This category features physics-based environmentals like Lunar Lander, which we'll look at further in a bit, and the bipedal walker, which require an agent to interact with simulated physical world. Toy text. Here we find text-based environments such as the frozen lake and taxi. These environments are excellent for testing decision-making in discrete action spaces. Mu-Jo-Ko, also called multi-joint dynamics with contact. These environments are like controlling a humanoid robot, providing complex simulations of robotic systems with multiple joints, focusing on realistic physical interactions. And finally, we have Atari. The Atari environment includes classical games such as Breakout, Pong, and Space Invaders, which are widely used to test deep reinforcement learning algorithms due to their complexity and variety. Some of the core features across all of these environments of the toolset provides three essential components. The environment is a simulated world where the agents interact. Next, we have observations. Information is received from the environment that helps the agent understand its current state. And finally, we have the actions, the set of possible moves or decisions the agent can make which directly impact the environment and determine the outcome of the simulation. Looking more specifically at Lunar Lander version 2, which was used for this assignment. Lunar Lander version 2 has a goal. The primary objective of the Lunar Lander environment is straightforward and challenging: to safely land the Lunar Lander between the flags. The targeting landing zone is centered at the coordinates 0, 0 in the X and Y plane. Successfully landing close to this center point without crashing is key to maximizing the score. For the observation, it utilizes an agent with 8-dimensional observation vector from the environment. This vector provides critical information, including the X and Y coordinates of the lander, which indicate its current position. Additionally, the vector includes the linear velocities in both the X and Y directions, allowing the agent to gauge its speed and adjust accordingly. The angle and angular velocity of the lander are also provided, which are crucial for maintaining stability during the descent. And then finally, there are two Boolean values in the vector that indicates whether each of the lander's legs is in contact with the ground, providing immediate feedback on landing attempts. Finally, there's the action. The action has 4 discrete actions it can choose from at each time step. These are do nothing, which lets the lander continue as it is on its current trajectory. Fire the left thruster to push the lander to the right. Fire the right thruster to push the lander to the left. And finally, fire the main thruster to counteract gravity and slow the descent. Each action directly affects the lander's motion and is critical for navigating the lander safely to the landing zone. It is also important to note that each action is discrete and only one action can be executed per step. For this assignment, we looked at the Monte Carlo model and we looked at a rule-based model that we set up ourselves. We set up the rules ourselves within Python in the Google Colab. For the Monte Carlo model, let's discuss this model first. In this model, the actions are chosen using a random uniform distribution. What this means is that each time step, the agent selects an action completely independent of the current observations. There is no consideration for the lander's position, velocity, or angle. As a result, the outcomes generated by the Monte Carlo model are highly unpredictable. Since the actions are random, the results can vary widely from one trial to the next, making it difficult to consistently achieve the desired goal, such as a smooth landing. It's important to note that the Monte Carlo model doesn't have the ability to learn or adapt over time. The actions remain random throughout, meaning that no matter how many episodes the model runs, it won't improve its performance. Despite these limitations, the Monte Carlo model plays a crucial role in reinforcement learning. It serves as a baseline for model comparison, providing a reference point to evaluate how much better a more sophisticated model, such as a rule-based model, can perform. Next, we'll look at rule-based models. Unlike the Monte Carlo model, the rule-based model selects actions based on specific conditions that depend on the observations received from the environment. For instance, if the lunar lander is tilting to one side, the rule-based model might fire a thruster to correct the tilt. This conditional approach results in very predictable outcomes. Given the same set of conditions, the model will always take the same actions, leading to consistent performance across all trials. However, like the Monte Carlo model, the rule-based model also lacks the ability to learn or adapt. The rules are predefined and fixed, meaning the model cannot improve its decision-making based on past experiences or outcomes. Overall, while the rule-based model offers more control and predictability compared to the Monte Carlo model, it still has its limitations. These two models together provide a foundation for understanding the benefits and drawbacks of more advanced reinforcement learning techniques. First, we will look at the Monte Carlo model renderer of one of the episodes of Monte Carlo. Of note, there is no feedback system for choosing the next step. Actions are taken regardless of the state of the lunar lander. This results in uncontrolled angle, horizontal velocity, vertical velocity, and angular velocity. Additionally, it is prone to crash. The random uniform distribution for action selection often results in catastrophic orientation and velocities resulting in crashes. Sometimes the model does get lucky. Here is another Monte Carlo model render. Occasionally the lander will get lucky and land within the landing zone. However, the landings cannot be duplicated despite having the same episode seed. Finally, we'll look at a rule-based model render. The rule-based model is responsive and takes actions based upon the conditions of the lunar lander observation. This enables control to be maintained over the lander and enable a softer or more controlled landing. Given the environmental seed, the rule-based system will perform the same way each time. However, this does not have the ability to improve or adapt. It is entirely dependent upon the level of detail of the rules created by the programmer. Next, we'll look at performance results. We'll look at two different ones, the first being without horizontal correction applied to the rule-based model. In this analysis, we're comparing two approaches to controlling the lunar lander in the version 2 environment. In the Monte Carlo model and a rule-based model, each of these models uses a different strategy for determining the actions lander. Let's look at the overall performance. The random Monte Carlo model had an average score of negative 218, with a standard deviation of 123. However, the rule-based model outdid it significantly, and although it has an average score of negative 132, it also has an exceptionally low standard deviation of practically zero. The box plot on the left clearly illustrates the variability in performance between the two models. The random Monte Carlo model shows a wide spread in its results, indicated by the length of the box and whiskers. This variability reflects the unpredictable nature of the random actions, leading to broad range of scores. In contrast, the rule-based model demonstrates extreme consistent performance with all scores tightly clustered around its average. This predictability is a result of the model's structured decision making. Looking at the histogram on the right, the random Monte Carlo model exhibits a dispersed frequency distributed across the range of scores, reinforcing its inconsistency. And if we look at the rule-based model, it is represented by a single towering bar, showing that nearly all episodes resulted in the exact same score. This again highlights the model's reliability. Looking at the hypothesis testing, it further validates these observations. We conducted a hypothesis test. The t-statistic came out to be negative 6.91, and the p-value was 6.5 times 10 to the negative 11. The negative t-statistic confirms that the rule-based model consistently outperforms the Monte Carlo model. The extreme low p-value indicates that the difference is statistically significant, meaning that the likelihood of this difference is due to random chance is virtually zero. Next, we'll look at another performance results, but this time we have horizontal correction added as an additional rule to the rule-based model. In this overview of the metrics, let's look at the key performance metrics. The random Monte Carlo model achieved the average score of negative 214, which is nearly the same as the previous score of negative 218, with a standard deviation of 126, which is also nearly the same as the previous standard deviation for the random model. In contrast, the modified rule-based model to include the horizontal correction achieved an impressive positive score of 95 average, with nearly non-existent standard deviation of 1.42 times 10 to the negative 14. The box plot analysis on the left visually demonstrates the difference in performance between the two models. The random Monte Carlo model shows its widespread in its results, with a large box and whiskers indicating high variability and inconsistencies in performance similar to the previous performance report. The enhanced model shows an extremely tight cluster, which is barely visible at the top of the plot due to its high consistency. Even every run produced nearly identical outcomes thanks to the effective integration of horizontal velocity. The histogram on the right is for the random model is nearly the same, but the rule-based model is still 100, but it is much higher at 100 or at 95. And then if we look at the hypothesis, we conduct a hypothesis. The t-statistic was negative 24, and the p-value was an extremely small 2.26 times 10 to the negative 61. The negative t-statistic clearly indicates that the rule-based model significantly outperforms the Monte Carlo model. The extraordinary low p-value confirms the difference between the performance between the two models that is statistically significant and is not due to random chance. So in summary, incorporation of the horizontal velocity adjustments to the enhanced rule-based model had led to a dramatic improvement in performance. This model not only outperformed the Monte Carlo model, but did so with remarkable consistency. The data clearly shows that the rule-based strategy, when properly refined, such as including horizontal correction, offers superior control and reliability in guiding the lunar lander to successful landings. The information for this presentation was gathered from the gymnasium.pharma.org website.